Every digital interaction you have, from scrolling on your phone to accessing cloud services, is orchestrated by an unseen army of microchips. These tiny, intricate components are the silent architects of our modern world, performing billions of calculations per second. But how are these marvels of engineering brought into existence? The manufacturing process is one of the most complex and capital-intensive endeavors known to humankind, a symphony of precision spanning hundreds of steps. Today, we'll peel back the layers to reveal the extraordinary journey from ordinary sand to the intelligent brains of our devices. Our journey begins not with rare earth metals, but with one of the most abundant elements on Earth, silicon. Specifically, we're talking about silicon dioxide, or common sand. However, the silicon used in microchips is no ordinary beach sand. It must be refined to an astonishing degree of purity, often reaching 99.9999999%, that's one impurity atom for every billion silicon atoms. This extreme purity is absolutely critical because even a single foreign atom can disrupt the flow of electrons, causing a defect in a microscopic circuit. Achieving this level of purification is the first monumental challenge. Once purified, silicon powder is melted at over 1,400 degrees Celsius. A seed crystal is then carefully lowered into this molten silicon and slowly rotated and pulled upwards. This process, known as the Czochralski method, allows the silicon atoms to align perfectly with the seed crystal, forming a single, massive cylindrical crystal, or ingot. These ingots can be over 2 meters long and weigh hundreds of kilograms. The precision required during this crystal growth phase is immense, as any irregularities can lead to stress points or defects in the silicon lattice, rendering large sections unusable. These silicon ingots are then meticulously sliced into thin, circular discs called wafers, typically less than a millimeter thick. Imagine slicing a giant salami with diamond-tipped saws to achieve perfect flatness and consistency. After slicing, these wafers undergo extensive polishing to achieve an atomic-scale smooth surface, free from any microscopic scratches or imperfections. These wafers are the foundation upon which hundreds, sometimes thousands, of individual microchips will be built simultaneously. The diameter of these wafers, commonly 300 millimeters, directly impacts the efficiency and cost of production. Before any circuit design begins, wafers enter the clean room, an environment meticulously controlled to prevent contamination. Clean rooms are classified by the number of particles per cubic foot of air. For advanced chip manufacturing, these are often Class 1 facilities, meaning fewer than one particle of 0.5 microns or larger per cubic foot. To put this in perspective, a typical office environment might be Class 100,000, and a human hair is about 70 microns thick. Technicians wear full-body bunny suits to trap even the tiniest skin flakes or dust. Contamination is the ultimate enemy, capable of destroying entire batches of chips. The most critical and complex step is photolithography, essentially photographic printing on a microscopic scale. A thin layer of light-sensitive material, called photoresist, is applied to the wafer. Then, using highly precise machines called steppers or scanners, an intense ultraviolet, UV, light shines through a reticle, a quartz plate containing the circuit pattern. The light hardens or softens the photoresist according to the pattern. This process is repeated dozens of times, layer by layer, to build up the chip's intricate architecture. The accuracy required is mind-boggling, often down to a few nanometers. After the photoresist is patterned, the unwanted material on the wafer is removed through a process called etching. There are two main types: wet etching, which uses liquid chemicals, and dry etching, which employs plasma. Plasma etching, involving ionized gases, offers far greater precision and is essential for creating the incredibly tiny features in modern chips. The hardened photoresist protects the underlying silicon in the desired areas, while the unprotected areas are etched away, carving out the microscopic trenches and channels that will form the chip's transistors and wires. This precision is vital for the chip's performance. Once etched, new materials need to be added to the wafer. This is achieved through deposition processes. Common methods include chemical vapor deposition, CVD, where gases react to form a solid film on the wafer surface, and physical vapor deposition, PVD, which involves sputtering atoms from a target material onto the wafer. These techniques are used to add layers of insulators like silicon dioxide, or conductive materials like copper or tungsten, which form the interconnects between transistors. Each layer must be uniform and precisely controlled to ensure proper electrical function and prevent short circuits. Silicon in its pure form is a semiconductor, meaning it can conduct electricity under certain conditions. To make it useful for transistors, its electrical properties must be precisely altered through a process called doping. This involves introducing a small, controlled amount of impurities, or dopants, such as boron or phosphorus, into the silicon lattice. These dopants create either an excess of electrons, N-type, or holes, P-type, allowing us to control the flow of current. Ion implantation is a key technique, where ions of dopant atoms are accelerated and shot into the wafer, creating specific conductive regions. The combination of photolithography, etching, deposition, and doping is not a one-time event. It's a cyclical process, repeated hundreds of times to build up the chip's complex three-dimensional structure. Each cycle adds a new layer, with new patterns, new materials, and new electrical properties. Modern microchips are not flat surfaces, they are intricate multi-story cities of transistors and wires, stacked vertically. A single advanced chip can have over 100 layers, integrating billions of transistors. This incredible layering is what allows for the immense computational power we see today. Throughout this entire fabrication process, meticulous metrology, the science of measurement, and inspection are paramount. After almost every major step, wafers are subjected to rigorous checks using advanced optical and electron microscopes, laser scanners, and electrical testers. Any deviation, however small, can render a portion or even an entire chip useless. These inline inspections help identify defects early, preventing costly mistakes further down the line. It's a continuous feedback loop, ensuring that the process remains within extremely tight tolerances, which is critical for achieving acceptable manufacturing yields. Once all fabrication steps are complete, the wafer is still a single piece of silicon containing hundreds or thousands of individual dies, the actual chips. Before they are separated, an initial electrical test, known as wafer sort or die sort, is performed. Tiny probes make contact with test pads on each die, applying power and signals to check for basic functionality and performance. Defective dies are marked, often with an ink dot, to be discarded later. This step efficiently filters out bad chips before further, more expensive packaging processes. The number of working chips, dies, obtained from a single wafer is called the yield. For a 300 mm wafer costing thousands of dollars to process, and containing potentially hundreds of chips, a yield reduction of just a few percentage points can mean millions in lost revenue. This is why contamination control, precision in every step, and thorough testing are not just engineering challenges but fundamental economic imperatives. The competitive landscape of semiconductor manufacturing is heavily influenced by a company's ability to achieve and maintain high yields, directly impacting profitability and market share. Good dies are then separated from the wafer using ultrafine diamond saws, a process known as dicing. Each individual die is then carefully picked and prepared for packaging. Packaging is crucial, it protects the delicate silicon chip from environmental damage, provides electrical connections to the outside world, and helps dissipate heat. The die is attached to a lead frame or substrate, and tiny gold or copper wires are bonded to connect the chip's pads to the package's external pins. Finally, the entire assembly is encapsulated in plastic or ceramic, creating the familiar black rectangular chip. Even after packaging, the journey isn't over. Each packaged chip undergoes a rigorous final test to ensure it meets all specified performance criteria, including speed, power consumption, and thermal characteristics. Chips are often tested across a range of temperatures and voltages to guarantee reliability under various operating conditions. Any chip that fails these stringent tests is discarded. The chips that pass are then sorted into different performance bins, such as different clock speeds for CPUs, before being shipped to manufacturers for integration into their final products. The continuous shrinking of transistor sizes, often measured in nanometers, is at the heart of Moore's law, which predicted the doubling of transistors on a chip every 2 years. Today's most advanced chips feature structures as small as 3 or 5 nanometers. To grasp the scale, a single human DNA strand is about 2.5 nanometers thick. This constant push for smaller features drives unprecedented innovation in lithography and materials science, but also pushes manufacturing costs higher. Building a new state-of-the-art fab, a semiconductor fabrication plant, can now cost over $20 billion. The choice of manufacturing node presents a fundamental trade-off between performance and cost. Smaller nodes, like 3 nanometers or 5 nanometers, offer higher transistor density, leading to faster, more power-efficient chips. However, they demand incredibly complex and expensive equipment, leading to significantly higher manufacturing costs per wafer. Older, larger nodes, such as 28 nanometers or 65 nanometers, are much cheaper to produce but yield less powerful and less energy-efficient chips. Companies must strategically decide which node is appropriate for their product, balancing cutting-edge performance with economic viability and market demand. As we push the boundaries of physics, chip manufacturing faces unprecedented challenges. The transition to even smaller nodes, like 2 nanometers and beyond, requires new materials, new lithography techniques like high-NA EUV, and even more stringent environmental controls. The sheer capital investment required for new fabs is escalating, leading to increased consolidation in the industry and growing geopolitical importance of semiconductor supply chains. The drive for innovation continues, but it's a constant battle against physical limits and economic realities, shaping the very future of technology and global power dynamics. The manufacturing of microchips is a testament to human ingenuity and precision engineering. From a handful of sand, through hundreds of meticulous steps in pristine cleanrooms, emerges a device capable of transforming our world. It's a process demanding immense investment, relentless innovation, and a global collaboration of scientists and engineers. Understanding this journey reveals not just the technological marvel, but also the economic forces and geopolitical implications that drive the industry forward. These invisible factories are not just building chips, they are building the future, one perfectly placed atom at a time. Thank you for joining us on this deep dive.